magnetism. So in other words, we can call this part 2 of our lecture series. Thank you very much. Today, we will be looking at DC motors. What is a DC motor? A DC motor is a device that converts electrical energy in a current system, a direct current system, into mechanical energy. Now, how does a DC motor operate? I mean, what is the working principle of a DC motor? It operates based on the principle that when a current carrying conductor is placed in a magnetic field, the conductor experiences what we call mechanical force. Now, according to Fleming's left-hand rule, this mechanical force is given as F equals to BIL. And of course, when we talk about Fleming's left-hand rule, we are talking about the index finger, the middle finger, and the thumb, which is this sign here. These represent Fleming's left-hand rule. What does this imply? That this thumb points to the direction of the force. This points to the direction of the mechanical field, while this points to the direction of the current flow. So, our force, is always in Newton. Now, when a DC machine is loaded either as a motor or as a generator, the rotor conducts what we call, the rotor conductor carries current. How does this operate? When you apply current to the conductors, there is flow of current from the rotor conductors. Now, these conductors lie in the magnetic field of the air gap. Thus, each conductor experiences a force. The conductors lie near the surface of the rotor as a common radius from its center. Hence, torque is produced at the circumference of the rotor, and the rotor starts rotating. So that's the working principle of our DC motor. It will be asked, what is a torque? A torque is the quantitative measure of the tendency of a force to cause a rotational motion. It causes what? A rotational motion, or to bring about a change in rotational motion. It is in fact the moment of the force that produces or changes a rotational motion. So we have this illustration here. And then this. And this. Of course, we will label this as our force. And also, this will be the angle. And like this, of course, when you verify the sign of this becomes F sine theta. So, mathematically, our torque, written as torque, is equal to F sine theta. F sine theta, where the theta is the angle between the mechanical force and the distance of separation. So, in order to establish the torque equation, we will consider the basic circuit diagram of a DC motor and its voltage equation. So, if this is our circuit diagram for the DC motor. We will call this the rainbows, the resistance of the motor. And then, if there is a supply here, that's the power supply. Of course, we also assume that this is our DC motor. So, we can call this section here the brush of the motor. Of course, you know, the motor, when it is connected and subjected to a magnetic field, we also have what we call the shaft. This is our shaft, and this is our load. This shall be the direction of current flow. And of course, you know that these are the terminals of the resistance, the positive and the negative terminals. This is still the same current flowing into our DC motor. When the armature of a DC motor rotates under the influence of the driving torque, of the driving force, the armature conductors move through the magnetic field, and hence EMF is induced in them as in a generator. The induced EMF acts in opposite direction to the applied voltage, so which is from henceforth and is known as the back or counter EMF. The back or counter EMF. What does this imply? The back EMF acts in opposite direction to the power supply. So it flows in opposite direction to the flow of the current from the power supply. So our equation, according to God, from this diagram is given as T, which is our torque, equals to K phi current. Here, K is our constant value. Phi here is the flux per mole. I is the current flowing in the conductor. We shall expatiate more on that as we proceed. So, also, our K, which is KE, is given as P Z divided by 2 pi A. What does these parameters signify? P here represents what? The poles. Z here represents the number of the conductors. And our A is the number of parts. The number of conducting parts. Of course, there are always 2 conducting parts. So, for a series motor, the flux produced in the field winding is proportional to the armature current which is given as T G is proportional, is directly proportional to the square of the current. This is for our series motor. Of course, the constant of proportionality here will be our K A. K is the constant of proportionality, which is given as Pz divided by 2 pi times E. Remember, we said the P is what the number of poles, Z represents the number of conductors, and our A is what the number of the conducting part. So what about the case of a shunt motor? For a shunt motor, our torque is proportional to current. For a shunt motor, our torque is proportional to the current, which is given as Tg equals to K I A. So you can see the difference between the series motor and the shunt motor. We have some types of DC motors. We have the separately excited DC motor, we have the shunt wound DC motor, the series wound DC motor, the compound wound DC motor, the short DC motor. But for the purpose of this class, we shall not go into the details of the types of motors. So let's take an example. For instance, of course, physics can never be complete without you carrying out mathematical gymnastics on the problems given. We apply this to solve problems. So, if we are given a question of this nature, so find the useful flux per pole on no load of a 250 volt, on no load of what? Of the 250 volt. So what that implies is that the supply voltage is what? 250 volt. Find the useful flux per pole on no load of the 250 volt. 6-pole shunt motor having wave connected armature winding with 110 tons. The armature resistance including brush is given as 0.2 ohms. The armature current is 13.3 ampere at no load speed of 908 radian per minute. How do we go about such question? From that question, you agree with me that the supply voltage is what? 250 volt. Now, also, the current is given as 13.3 amperes. The number of poles, of course, we told that there were 6 poles. So, P will be 6. The number of tons, which represent the number of conductors, is given as 110 tons. So, since there are 110 tons and there are 2 conducting parts, so we multiply this by 2. And that gives us what? Z equals to 220 tons. Also, the speed is given as, which is m, 908 radian per minute. So, from the parameters given to us, Of course, you know that back EMF. Our back EMF is always less than the power supply. That's the potential difference connected to the circuit or across the circuit. So, if this is what we have as the potential difference, it therefore means that for us to calculate the EMF voltage, we can use EB to represent the back EMF. That will become equals to 215 minus the current given as 13.3 ampere multiplied by the resistance, which is given as what? 0.2 ohms. So that becomes equals to what? To 247.36 volts. So these represent what? The back or the counter EMF. Now, if you recall from our diagram, you will agree with me that our back EMF is P phi NZ divided by 16A. This P represents the moles. This is flux per mole. N represents what? The speed of the motor. Z represents what? The number of what? Of conductors. A here represents what? The number of the conducting parts. Now, if we have this as the formula, remember, we are asked to calculate what? Because it says find the useful flux per pole. So, our interest is on the flux per pole. So what do? Of course, we will apply what we call change of subject or formula. What do we do here? We cross multiply. So when we cross multiply, that becomes EB times 16A equals to what? P 5NZ times 1. Because there's 1 there. So if that is okay, our interest is to find phi. That is what? The flux per pole. So what do? We divide both sides by the coefficient of flux per pole. So we divide all through by what? P and Z. P and Z. So when we do that, P will cancel P, N will cancel N, Z will cancel Z. And our equation will now become 5 equals to EB times 16A divided by P and Z. So, from this formula, we can use this to determine our flux per pole. So that this becomes, what is our back EMF? The back EMF is given as 247.36 multiplied by 60 multiplied by A. A we say is what? The number of the conducting parts, which is 2. All divided by what? Our P. What is our P? Our P represents the number of poles. So that would be 6 times, what is our N? Our N is 908 RPM multiplied by our Z. What is our Z? 220. So, when we carry out this multiplication and addition, our answer will be 24.8 million W. That is our flux per pole. So, you can see before the board that this is how you can determine what flux per pole. And always have it at the back of your mind that the EMF, the back EMF, is always less than what the supplied voltage. Alright, we'll be switching gears to another subtopic. And this time around, we'll be looking at what? Electromagnets. Electromagnets. What are electromagnets? An electromagnet is a type of magnet that is made of coils of wire with electricity passing through them. Now, what does this imply? What this implies is that this electromagnet can only function as magnets when electricity is supplied to them. Once you cut off the supply of electricity to them, they are no longer what? Magnets. And so that's why we say that the main advantage it has over a permanent magnet is that the magnetic field can be quickly changed by controlling the amount of electric current in the winding. So what that implies is, since the magnetic field is determined by the electricity flowing through the magnet, it therefore implies that we can control the amount of electric current, or we can control the changing magnetic field based on the amount of current supplied to the circuit. They are widely applicable in generators, motors, relays, loudspeaker, and so on and so forth. So they have their wide range of applications. We will also treat another subtopic. This time around, it will be carbon microphones. Carbon microphones. Of course, I am using the microphone to teach you. So this makes our lecture easier for us. And if I may ask, what's a microphone? A microphone is an example of a transducer. And a microphone is an example of a transducer. What is a transducer? A transducer is a device that converts energy from one form to another. It converts what? Energy, or that is signal from one form to another. So, in this case, what's a carbon microphone, or what's a microphone? A microphone is a device that converts sound energy into what? Electrical energy. Example, I am talking to you right now. This microphone can convert, or is converting this sound energy. What I'm saying, my voice, is converting into electrical energy. Now, what are the qualities, or what are the characteristics, or what constitutes a good microphone? One, a good microphone must have high sensitivity. A good microphone must have high signal to noise ratio. It must have a flat frequency response. Of course, you know that the audible range, the audible frequency range is what? Is from 16 hertz to 20,000 hertz. What does this imply? That an average human ear can hear a sound within the range of 16 hertz to 20,000 hertz. Of course, there are ranges for other animals, but for human beings, this is our range. This is the maximum range we can get. It must also have what? Natural resonant frequency outside audible range. It must have low distortion. There shouldn't be what distortion when using the microphone. Of course, I expect the feedback from you if we are having distortion. Distortion, noise. If there are distortion, if you can't hear well, of course you know that this may not actually be what a good microphone. It must also have what output impedance. The output impedance must match line impedance. So, the carbon microphone, how does it work? How does it work? How does the carbon microphone work? Sound hits what? The carbon granules and exert a pressure on it. Now, this varying pressure is converted to what? To varying resistance. The varying resistance causes what? Distortion or changes the flow of current. So it is like that it is what transferred to either what a capacitor or some other device. Having talked about the carbon microphone, we switch gears again. This time around, we'll be looking at another subtopic, which is the moving coil and moving iron instrument. The moving coil and the moving iron instrument. The moving coil and the moving iron instrument. These are all measuring devices or measuring instruments that are employed to measure either our power or our voltage or our current, depending on the variable that we are looking for. So the moving coil instrument is a very commonly used form of analog voltmeter because of its sensitivity, accuracy, and linear scale, although it only responds to DC signals. We can find them in our laboratories. For those of you that go to the lab to carry out your experiment on also, you must have come across our measuring instrument, your voltmeter, your ammeter, your galvanometer, and all of that. They are all measuring instrument. And when a DC supply is given to the moving coil, DC current flows through it. When the current carrying coil is kept in the magnetic field, it experiences a force. This force produces a torque, and the former rotates. The pointer is attached to the spindle. When the former rotates, the pointer moves over the calibrated scale. You see how it works? When the former rotates, the pointer moves over the calibrated scale. When the polarity is reversed, a torque is produced in the opposite direction. So that is what is the working principle of a moving coil instrument. The amount of rotation of the coil is measured by attaching a pointer to it that moves past a graduated scale. So you can see that when we have our ammeter or voltmeter, for instance, the amount of the rotation of the coil is measured by what? By attaching a pointer. When that pointer moves as you're taking your reading, that pointer measures what? It measures what the amount of rotation of the coil. The theoretical torque produced is given by T equals to B I H W all in Newton. So where B is the density of the radial field. B is the density of the radial field, like the magnetic field. I is what? Is the current flowing in the coil. H is the height of the coil. W is the width of the coil. And our N here represents what? The number of turns in the coil. Now we move to the next one, which is the moving coil, the moving iron instrument. We have discussed the moving coil. Now we are now talking about the moving iron instrument. It is usually used to measure alternating voltages and current. You know, in a moving coil, it is basically used or applicable for DC voltages or DC current. But in our moving iron instrument, it is usually used to measure what? Alternating what? Voltages and current. The signal to be measured is applied to a stationary coil, and the associated field produced is often amplified, or what we say often increased, by the presence of an iron structure associated with the fixed coil. The moving element in the instrument consists of an iron vein suspended within the field of the fixed coil. When the fixed coil is excited, the iron vein turns in a direction that increases the flux through it. So, that is the working principle of our moving iron instrument. The torque produced that causes the vein or the van to turn is given as torque produced here is given as I squared L, all divided by 2 theta. Where the M is what? The mutual inductance. Theta there is the angle between, or is the angle, or is the angular deflection. The angular deflection. Now, we will focus on the conversion of galvanometers to ammeters and to voltmeters. The conversion of galvanometers. Conversion of galvanometers. Conversion of galvanometer to ammeter and voltmeter. Conversion of galvanometer to ammeter and voltmeter. What is a galvanometer? A galvanometer is a device used to find direction of current and its magnitude. A galvanometer is used to what? To find the direction of current and its magnitude. It has small resistance and is usually connected in series. A galvanometer has a very tiny resistance and is usually connected in series in our circuit. Always connected in series in our electric circuit. A galvanometer can detect only small current. Now, this is the disadvantage of using what? A galvanometer only. When you use only a galvanometer, when taking measurement, you have to take cognizance of the fact that only a small current can be detected by our galvanometer. So, how do we improve on our galvanometer? And that takes us to our conversion of galvanometer to ammeter. That takes us to the conversion of galvanometer to ammeter. In order to measure large current, a galvanometer is converted to an ammeter. Now, we have always said a galvanometer can only measure small current. So, if we have a situation in which we want it to measure large amount of current, what do? We convert it to the ammeter. So we take this conversion of the galvanometer to ammeter. So, in order to convert our galvanometer to ammeter so that we can measure any amount of current, we simply connect our galvanometer in parallel with a low resistance called shunt resistance. Take note of it. Shunt resistance. So, conversion of galvanometer to ammeter can only be made possible by what? By connecting our galvanometer in parallel with what? A low resistance called what? Shunt resistance. So, how is that done? Okay, let's take an illustration of this connection. Let's call this here our shunt, okay, connected in parallel with our galvanometer. Of course, if this is the direction of current flow, so we call this current. Now, when the current flows to this point, there are two terminals here, 2 points here. This current will continue flowing this way, and it will also continue flowing this way. But we know that the current here is what? The current of the galvanometer. Now, how then do we determine the current flowing here? That is the current flowing into the shunt resistance. Of course, by our principle of Kirchhoff's current law. Of course, I understand that Kirchhoff's current law is not for your level. But in electronics, we have what we call Kirchhoff's current law, which says that current flowing around a circuit That is the algebraic sum of current flowing into a circuit is equals to 0. So what that implies is that the sum current flowing into a circuit is equals to what? The sum current flowing out of the circuit. So when you watch carefully here, you'll see that I is flowing into the circuit. So let's call this IS. So if that's our IS, so for this current flowing in, we call it I equals to IS plus IG. So the current IS, which is our shown current, so now we call it what? I minus IG. So here will be written, instead of IS, we write I minus IG. So that's the current that flows into what? Into the shunt resistance. And of course, this is still our galvanometer current. Good. So, how do we determine the effective resistance? How do we determine the effective resistance? If you recall vividly from your electricity, you were taught connection of resistors in series and in parallel. But before we dive into that, let us work on the potential difference. Now, see part of that. Recall, you were told that when two resistors or more are connected in parallel, the potential difference is always what? The same. Potential difference is always the same. So if potential difference is always the same, it therefore means that the potential difference of the shunt resistance will be equal to what? The potential difference of what? Of our galvanometer. Now, looking at this equation, how do we determine the potential difference of the shunt resistance? Recall again from our Ohm's law. According to Ohm's law, V is equal to IR. So if that is what we know from Ohm's law, so instead of writing Vs, we will now write Vs equals to what? Current and the resistance of the shunt. Of course, we said the current entering the shunt is what? We say the current entering the shunt resistance is I minus Ig. So this becomes I minus Ig, all multiplied by the shunt resistance. What about the galvanometer? The potential difference of the galvanometer is given as what? Ig multiplied by Ig. So, equating these two together, our equation will now become I minus Ig into Rs is equals to Ig Rg. So, in order to simplify this equation further, since we are looking for the resistance of the shunt, of course, we make this a separate formula, and that becomes Rs equals to Ig Rg divided by what? I minus Ig. So this is the expression for the shunt resistance. So when you're converting your galvanometer to ammeter, you connect what? The galvanometer in parallel with the shunt resistance. We can also determine the current of the galvanometer. Of course, from this equation, what will be our current of the galvanometer? So what we simply do here is to come back to this step. I minus Ig, all multiplied by Rs is equal to what? Ig. So what do? We open this bracket. So it becomes Irs minus Rs, and that becomes equals to Ig. Recall, we are looking for what? Ig. So what do? We collect like terms. So if you look at this left-hand side equation, this becomes I. That becomes Rs equals to, if this crosses this equality side, this negative side becomes what? Plus. So it becomes plus Ig plus what? Rs. So Irs becomes equals to, of course, if you look at the right hand side of this equation, you see a common term there. What is the common term there? Ig. So this becomes Ig into what? Ig plus Rs. So making Ig the subject of formula, Ig becomes equals to what? Rs divided by Ig plus Rs. So this is our relationship or equation for determining the current in the galvanometer, and this is to find the shunt resistance. So how do we determine, or how do we convert our galvanometer to voltmeter? For instance, we say the galvanometer only detects what? Very small amount of what? Of current. Same thing with the voltage. So you are presented with a galvanometer and a voltmeter, and you are told to use a galvanometer and a voltmeter to ensure that the readings improve. What do? You connect your galvanometer in series with what? With your voltmeter. You connect your galvanometer in series with a high resistance. In this case, we call it a multiplier to show you how much it is. We use a multiplier. So, for conversion from galvanometer to voltmeter, conversion of galvanometer to voltmeter. So we say galvanometer can be converted into a voltmeter by connecting with a high resistance. Connecting it with what? A high resistance. Potential difference across a given low resistance is the sum of the potential difference across the galvanometer and the potential difference across the high resistance. So we can connect that. This is our galvanometer connected in series with what? With a high resistance. So, this is our current flowing. This is the galvanometer current. And of course, we can call this our V. So, for this case, V will be equal to Ig into what? The resistance of what? Of the galvanometer plus the high resistance. Remember we said we are looking at the potential difference. When we equate those two, you have this. So this is a potential difference. And from here, we can determine I by making I the solid formula, that is V equals to Ig Rs plus Ig R. And of course, this becomes V minus Ig Rs divided by V minus Ig Rs equals to Ig R. Of course, making R the solid formula, we divide both sides by Ig. So R will be equals to V over Ig minus Ig Rs divided by Ig. So, when we do that, our R becomes equals to V over Ig minus Rs. So, this is the relationship. And this is how to determine this resistance in the circuit. So, we'll take some examples. Example 1. The question says, what shunt resistance is needed to make 1 milliampere 20 ohm galvanometer into an ammeter with a range of 0 to 50 milliampere? That's in question 1. 2. Find the resistance of the ammeter. From the question given, we are told that the galvanometer current is given as what? Ig equals to 1 milliampere. Also, the resistance of the galvanometer is given as what? 20 ohms. flowing in a circuit is given as I equals to what? 15 milliampere. Based on the range, so we are picking the maximum from the range given to us. The range is from 0 to 50 milliampere. So the current when the circuit will be what? 50 milliampere. So based on the equation derived for conversion of galvanometer to ammeter, we know that the resistance of the galvanometer is given as what? The current of the galvanometer divided by what? The current in the circuit minus the current in the galvanometer multiplied by what? The resistance of the galvanometer. So, looking at what we have here, looking at these parameters and the parameters given in the question, we can simply make it. Because the idea is to what? Is to calculate the resistance, the shunt resistance. So, we simply substitute the values. The current in the galvanometer is 1 milliampere. Of course, 1 milliampere is same as 1 times 10 to the power minus 3 ampere. So this is same as saying 10 power minus 3 ampere. For this, 50 milliampere will be what? 50 times 10 to the power minus 3 ampere. And that is equal to what? 50, so that we can have that 50 times 10 to the power minus 3 ampere. We now substitute these values into this equation. So our IG, our shunt resistance will be what? 10 to the power minus 3 divided by our current flowing in is what? 50 times 10 to the power minus 3 minus 10 to the power minus 3, which is the current in what? In the shunt resistance. All this multiplied by the resistance of the galvanometer of the galvanometer given as 20, this is RG, given as 20 ohms. So this becomes what? 10 to the power minus 3 divided by, of course, we have 10 to the power minus 3 here and 10 to the power minus 3. So we can simply say 50 minus 1 all times 10 to the power minus 3 times 20. Because they are set like terms. So we pick the common term. So, how can I arrive at that? If you look at this equation, you'll see that we have 10 to the power minus 3 up and 10 to the power minus 3 down. So, we can say that this 10 to the power minus 3 will cancel 10 to the power minus 3 here. And that becomes equals to 1 over 50 times 20. Of course, 50 minus what? 50 minus 1 is what? 49. And that becomes equal to what? 20 divided by 49. And that gives us what? 0.40 ohms. So this is what? Is the shunt resistance. The second question says, find the resistance of the ammeter. Find the resistance of the ammeter. The resistance of the ammeter, of course, from our diagram, is given as what Rg times the resistance of the shunt, all divided by what? The galvanometer resistance plus the shunt resistance. Of course, when they are connected in parallel, when resistors are connected in parallel, what do you do? For you to find the effective resistance, just as we have in our diagram, for you to find the effective resistance of those resistors, for two resistors, you say 1 all over what R effective equals to what? 1 over Rg plus 1 over Rs. Of course, this becomes 1 over R effective equals to what? The LCM of Rg and Rs is what? Is Rg Rs. So this is our LCM. This divided by this you have what? Rs. Rs times 1 is what? Is Rs plus Rs. This is the LCM. LCM divided by this is what? Is Rg. Rg times 1 is what? Rg. So that 1 over effective resistance is equals to, of course, we can switch the position to be what? Rg plus Rs all divided by what? Rg Rs. Well, remember, we're looking for the inverse of the effective resistance. We're looking for what? For the effective resistance. So what do? We cross multiply. So that becomes what? Rg Rs is equals to R effective multiplied by Rg plus Rs. So R effective is equals to what? Rg Rs all divided by what? Rg plus Rs. And this is what we call the resistance of the ammeter. So when you compare this equation with this, you see that we are correct. So this is how to determine the effective resistance for a parallel connection. Yes. Now, having done this, we substitute the values into this equation so that Ra will become equals to what? What is our Rg? It's given as 20 ohms multiplied by Rs that we just saw and we got what? 0.4. All divided by what? Rg, which is 20 plus Rs, 0.4. And that gives us what? 20 times 0.4 gives us what? Gives us 8. 8 divided by what? 20.4. And that is equals to what? 0.39 ohms, which is equivalent to what? Or approximately to 0.40 ohms resistor. So, how to handle a problem related to a galvanometer connected with an converted to an ammeter? We'll also look at another problem that is related to galvanometer conversion to a voltmeter. The question is, how can we make a galvanometer with resistance of 20 ohms and a full-scale deflection current given as 1 milliampere into a voltmeter with a maximum range of 10 volts? So you can see, the voltage is very high. How then do we convert our galvanometer to suit that purpose? Of course, we know from our understanding of conversion of galvanometer to voltmeter that the galvanometer is usually connected what is series with a high resistance called a multiplier. So in this case, from the question we are given that V is equal to what? Is equal to 10 volts. That's the potential difference, or the maximum range. And our current of the galvanometer is what? Is given as 1 milliampere. Our resistance of the galvanometer is given as 20 ohms. So we have to find what? We have to find the resistance of the multiplier that will withstand this high voltage, which is R. So we call it R, equals to, we don't know. So we have to add, we have to find it. And we know from our equation that R is given as what? V over Ig minus Rs. From our equation that we derive. So this becomes what? What is our V? 10 volts divided by the current in the galvanometer, which is what? 10 to the power minus 3. Of course, you know, when you convert this becomes 10 to the power what? Minus 3 ampere. The voltage is 10 megavolts. 10 megavolts. Let's look at the question. The question says, how can we make a galvanometer with resistance of 20 ohms and full-scale deflection current of 1 milliampere into a voltmeter with a maximum range of 10 volts? So it's 10 volts, not 10 megavolts. So we stick to our 10 volts. So the resistance of the shunt is given as what? 20 ohms. So this becomes equal to what? 10 divided by 3 divided by minus 3. Of course, you were told in your indices that when you have an equation of this form, A divided by A to the power minus 2. You know that we have same words, base. They are the same bases here. And A is the same as what? A is the power what? Of 1. And anything raised to the power of 1 is what? Is that same number. Good. How can I establish that? Now, since they are the same bases, what do? We take this power out. So that becomes, this becomes equal to what? A to the power of 1. As this minus sign crosses this division sign, it becomes what? Plus. That becomes 1 plus 2. And that equals what? A to the power of 3. Good. So, if that is accepted, we can therefore apply same method here. So 10 divided by 10 to the power minus 3 is same as saying 10 to the power of 1 plus 3 minus 20. And that gives us what? 10 to the power of 4 minus 20. And that gives us what? That becomes 9.980. Okay, let's do that. 9.98 kilo ohms. So that is the resistance that is required to convert our galvanometer to a voltmeter that has a maximum range of what? Of 10 volts. Sensitivity of the galvanometer. What is the sensitivity of a galvanometer? The sensitivity of a galvanometer is the angle of deflection per unit current flowing through it. The angle of deflection per unit current flowing through it. Sensitivity of a You say it is what? The angle of deflection per unit current flowing through it. So, if delta theta is changed in the deflection produced by a small change in the current, we can represent that small change in the current as delta I. Or delta I. So if that is it therefore means that the sensitivity of the galvanometer will be given as what? Delta theta over what? Delta I. So this is what we call what? The sensitivity of a galvanometer. So that the current flowing through a moving coil galvanometer, the current flowing through the galvanometer will be given as I equals to what? K over N A B theta. Sorry, this theta is always here. That is the current flowing through it. So what does this parameters represent? The I is what? It is the current flowing through it. The K is what? K is the couple per unit twist. Theta is the angle of deflection. N is what? Is the number of turns. N is the number of turns. A is the area. And B is what? Is the magnetic induction. A is the area and B is the magnetic induction. So, if we make theta the subject of formula here, therefore this equation now becomes theta equals to N A B divided by K times I. You see, when you make theta such a formula, that becomes NAB over K times I. Now, we apply a little of calculus differentiation. If we differentiate both sides, or before doing that, if we divide both sides by I, this becomes theta over I equals what? N A B over K. Finding the differentiation, that becomes the theta over the I is equal to what? N A B over K. Where the theta over the I is what? Is the sensitivity of the galvanometer. So this equation will now become S equals to N A B divided by K. This is the sensitivity of the galvanometer, or how you can quantify the sensitivity of a galvanometer. So let's take an example. Question says, what is the sensitivity of the galvanometer inside a voltmeter that has a 1.0 mega ohms resistance on its 30.0 volt scale? How do we determine the sensitivity of such galvanometer? We know that from our Ohm's law, the divided by of the scale divided by the resistance. So this becomes what? What is our potential difference given there? Say 30.0 volts divided by our resistance, which is what? I is given as R is given as 1.0 mega ohms. And our voltage, full scale differential, is given as 30.0 volts. Of course, 1.0 mega ohms is equivalent to what? 10 to the power of 6 ohms. So this becomes 30 divided by 10 to the power of 6 ohms. And if you multiply, if you divide that, that will give you what? 30 microampere. So that is what is the sensitivity of that galvanometer, or we can say it is the current that gives full scale deflection of 30 volts when connected through a 1.0 mega ohms. So we will conclude the class for here, or we'll end the class here today for this aspect of this course, and hopefully we are going to treat the part 3 of this course. Thank you very much for your time. Thank you.